Morning everyone. Today I'll be talking about TCP and quality of service and how they work together to deliver predictable network performance. Modern networks carry very different type of traffic, video calls, file downloads, gaming, cloud applications, all sharing the same infrastructure. This seminar explains why congestion happens, how TCP reacts to it, and why QoS needed to meet the real world performance expectations. Why traffic management matters? Traffic management matters because network demand has grown rapidly due to streaming, conferencing, and real-time apps. These applications require low latency and stable bandwidth, but network resources like links and buffers are limited and shared. Without proper traffic management, aggressive flows dominate, leading to poor user experience. So the goal is fairness, efficiency, and predictable performance. Communication model recap. That's a recap, sender to receiver. The internet follow a packet switched best effort delivery model. Packets move from sender to receiver without guarantees. The network core simply forwards packets and does not control congestion itself. Because of this design, congestion control responsibility falls mostly on the endpoints, especially TCP. Okay, now we are going to see what is network congestion. Network congestion occurs when offered traffic exceeds forwarding capacity. We observe it through rise queue lengths, increased delay, packet drops, and retransmissions. The root causes buffer overflow at routers. Congestions can be mitigated at multiple layers. Transport protocols like TCP, queue scheduling, and admission control and diagnosed using metrics like RTT and loss rate. Let's see what are the causes of congestion. Congestion arises due to network level causes like bandwidth mismatch and limited buffer sizes. Traffic level causes include bursty applications and uncontrolled senders. Operational mitigations involve monitoring at network edges, traffic shaping, policing aggressive flows, and properly sizing buffers. So congestion is both technical and operational challenge. Effects of congestion on network operations. When congestion occurs, end-to-end delay increases. Effective interactive applications like VoLP, packet loss forces retransmissions, reducing effective throughput and wasting bandwidth. Severe congestions can cause collapse where throughput drops dramatically. Additional router experiences higher CPU and memory usage, increasing failure risks. Why congestion control is essential? Congestion control stabilizes network traffic and prevents collapse when many senders compete. It ensures fairness, so no single flow dominates. It also supports predictable service levels and reduces operational incidents. Without congestion control, shared network would be unusable at scale. So let's see about transport layer. Transport layer, edge congestion control. TCP implements congestion control at network edge. The sender monitors AKS, loss, and RTT to infer network conditions. Based on these signals, it adjusts its sending rate dynamically. This keeps the network core simple and scalable. Let's see about TCP connection reliability and adaptive sending now. TCP establishes connection oriented and session guarantees reliable order delivery. It detects loss using AKS, ACK, and timers. Retransmits missing data and dynamically adjusts its congestion window. This adaptive behavior allows TCP to respond changing network conditions. Let's see about congestion window. Congestion window or CWND. The congestion window controls how much data can be in flight. Actual sendable data is limited by minimum of congestion window and receiver window. RTT and packet loss directly influence congestion window growth and reduction. This mechanism is central to TCP congestion control. Let's see TCP's congestion control phases. TCP operates in phases: slow start, congestion avoidance, fast retransmit, and fast recovery. Each phase represents a different strategy of probing capacity and reacting to loss. Together they form a continuous control loop for managing congestion. Let's see about TCP's slow start. TCP slow start. Slow start begins with small congestion window. The window doubles every RTT rapidly, probing available bandwidth. Once the threshold is reached or loss occurs, TCP exits slow start. While effective, it risks overshooting capacity. Let's see about congestion avoidance. Congestion avoidance. In congestion avoidance, congestion window increases linearly instead of exponentially. This causes growth probes additional capacity while maintaining stability. The AIMD principle governs this behavior, ensuring fairness across flows. Okay, what is AIMD principle? AIMD, additive increase, multiplicative decrease. Additive increase slowly raises control window to test capacity. Multiplicative decrease rapidly reduces control window upon packet loss. This balance achieves stability, fairness, and responsiveness. AIMD is foundation of TCP congestion control. Let's see about packet loss detection. Packet loss detection. TCP detects packet loss using timeouts and duplicate acknowledgements. Most losses are treated as congestion by default. However, distinguishing congestion from link errors require cross-layer diagnostics. Correct interpretation is crucial before tuning parameters. Okay, what is fast retransmit? Fast retransmit. While multiple duplicates ACKs are received, TCP triggers fast retransmit. This allows lost packets to be resent without waiting for a timeout. It significantly reduces recovery time and improves throughput. Fast recovery. In fast recovery, TCP reduces controlled window but continues transmission. This avoids restarting slow start completely. As a result, throughput remains steadier after packet loss. TCP's strength and limitations. That's the next topic. Yeah. TCP is reliable, adaptive, fair, and widely deployed. However, it assumes all losses, indicates congestion, and lack traffic prioritization. It cannot guarantee strict latency or application SLAs. This is where QoS becomes necessary. Okay. Why adopt quality of service? Quality of service ensures the right performance for each application. It protects delay sensitive traffic, reduces loss for critical flow, and differentiates services by priority. Quality of service implements TCP where transport level control is alone insufficient. Key QoS parameters. Here QoS means quality of service. Key QoS parameters include bandwidth, latency, jitter, and packet loss. Each metric impacts user experience differently. Monitoring these parameters is essential for enforcing SLAs and tuning policies. Quality of service mechanisms. QoS works through classification, policing, shaping, scheduling, and reservation. Traffic is identified, controlled, queued, and prioritized based on requirements. Together, these mechanisms enable predictable performance. Next, we will see about comparing and queuing techniques. FIFO is simple but offers no prioritization. Priority queuing provides low latency but risks starvation. Weighted fair queuing balances fairness and delay. The choice depends on application requirements. Let's see TCP and QoS working together. TCP adapts sending rates and based on network feedback. QoS policies manage packets within the network together. They protect multimedia flows and prevent counterproductive interactions. So, real world applications of these: video streaming. Video streaming prioritizes steady throughput, VoLP and conferencing, demand low latency and jitter. Gaming and backbone networks require rapid recovery and consistency. Each use cases needs tailored TCP and QoS policies. Conclusion: bringing TCP and QoS together. To conclude, congestion is unavoidable but manageable. TCP provides adaptive congestion control while QoS ensures differentiated delivery. Combining measurement, classification, and queue management produces predictable outcomes. The key is continuous monitoring, tuning, and validation. That's it, guys. You have now completed TCP and QoS.